Alright, so for number 6, if you got B, I know exactly what you did wrong. Okay. Alright. Square roots of x can turn to x to the 1/2, right?
Yes.
Okay. I recommend you do that part first before you start moving. Because then it makes it a little easier to see that that's the only thing that needs to come up. Numbers can stay put. Okay, that's the only thing that has the 1/2 on it. So I'll rewrite that as 2x to the 1/2 minus 1/2 x to the negative 1/2. I'll have an extra fraction bar in there, but that's okay. I know what I'm trying to do. Okay. So our derivative, 1/2 comes down, multiplies the 2 to give you 1, bless you. X to the 1/2 minus 2/2 is negative 1/2. Negative 1/2 comes down to multiply, negative 1/2 is going to give us a positive 1/4. X to the negative 1/2 minus 2/2 is negative 3/2. Okay? And so then you look, because in this packet sometimes they leave stuff with the negative exponents, but it doesn't match B. So let's rewrite it. The other answers are all in radical form, so we know we're going to go to radical form. Goodness gracious. So this is going to drop to the bottom as an x to the square root of x minus 1/4. If you need to think about negative 3/2 as negative 1.5, think of it that way. Okay, both pieces are negative, so the x to the negative 1 drops down as an x to the positive 1, and the 1/2 drops down as a square root. They're both negative, if you need to think of it like that. Okay?
Where'd you get one?
The negative 1/2 came down and multiplied the negative 1/2.
Wait, why did it go down?
Huh?
So, isn't that the
It's the power rule.
power rule? But then, so I got everything up to there.
Did you get to here?
Huh?
Did you get to here?
Okay, I got the first part of the answer correct. Like
Here?
the first part. No. What I'm saying is like the 1x. Yeah, that part I got right.
Okay.
But somewhere I got lost.
All right. Do you have the 1/4?
No, I have 1/2.
1/2. My guess is then that you didn't bring this negative 1/2 down and multiply that 1/2. Negative.
Did you not have a negative 2?
This 2 doesn't have it's an understood 2 to the positive 1. It stays down in the bottom.
No, I'm talking about. Is that all?
Yeah.
You do the product rule, right?
No.
No.
Constant multiple rule. Look at it like this, okay? If you need to look at it like this, we'll do this. Come on. Let's just pull that piece of it off to the side. Well, that's not what I meant to do, but okay. Let's just look at this piece,
Okay.
okay? All right. Are you okay with this?
Yeah,
Okay, think of it like that, because this is just a number. Okay, so it just tags along. Okay, and then it had a negative in front of it. Okay?
Okay, because I did a whole negative.
I mean, you can do the product rule here, but when you get to second times derivative of the first is 0, so it should have gone away.
What I did was, that's where I messed up, I put it negative 1. I don't know why.
If you put negative 1, it means that you brought the 2 up.
Yeah,
But that's a 1/2, it's not a 2.
yeah.
Okay? So if you need to think about pulling it off and just looking at it like that, Do it that way. That matches choice D.
Can you say one more time how you got the 1/4 square root of x?
Here,
Yes. How'd you get that?
let's think of it this way. If I bring this down like that, are you okay with that part? It's just switching it. 3/2 is 1.5. One and a half. And go like that. Okay. All right, 7 was A. They were weird. They just replaced that square root thing with Y. But after doing implicit differentiation, then that should not be as weird as it would have been before. Anybody need to talk about number 7?
Yeah.
Okay. I'm going to go ahead and put that to the 1/2 power. Are we okay? So this is just a chain rule. I don't know that I'd introduce a logarithm because it's just one chain rule. It's not mixed in with a product rule, quotient rule, other chain rules. So our derivative, bring the 1/2 down, leave the inside alone, decrease our exponent by 1, times the derivative of the inside, which is going to be 2x plus 2. So far, so good? Alright, so we got a 1 times 2x plus 2 in the top. And we've got a 2 times that comes down under a square root. We okay there so far? And what they did was they factored out a 2, or you could think of it as distributing that 1/2, whichever one kind of makes you think about it better. So far I've not written that yet. And so that allows us to cancel that out. So when I look at the choices so far, the x plus 1s in the numerator is either going to be A or D, correct? I know I've got this square root thing left, and it's a square root. It's not a 3/2 like in D. So then I have to say, why in the world is that thing suddenly Y? But remember, Y was that thing. So that's what they did. It is tricky. Try to see. We're smarter than they are. We know how to put their things. All right, 8D. Questions on 8? Anybody? Quotient rule. You notice how it's easier to recognize the quotient rule than it is the product rule? We just skim right by the product rule all the time. I think it's in our inherent dislike of fractions. We see them and they just inherently register in our brain. Oh, it's okay. Alrighty.
Can you go back to 6 so I can just look at it?
Can you do what? Go back to 6.
Make it bigger.
Let's see. Do you want the pink part, the black part, or the purple part? Because we thought about it in 3 different ways.
Pink part.
The pink part. Anybody else going to be upset if the other stuff goes away? You look at that, and I'll do the handouts. Yeah, in the applications unit, you are welcome to use the drafting calculators at any time. And I didn't realize until I made the copies that I didn't put in the page that had the assignment on it. So you'll have to look on the block of that page.
No.
In this one?
Yeah.
Is it supposed to be there?
You've seen the middle schoolers throw stuff about on their stairs. I don't know why I was listening here. I don't want to
No, that would make me sad.
I forgot. Yes, they are. We have to work with them. No, this morning.
It's like it's just interesting because it's like
Everybody get one?
I think it's just because I ended up with something. I like coffee like this.
I never know who wants theirs stapled or not, so. I was putting mine in a 3-ring binder, it makes me crazy to staple it, so.
Oh,
I
yeah.
staple it in a book because it makes me
How'd it go where? Here?
Yeah.
A negative times a negative.
You see where I'm listening? I don't see it. Like, I got that. Like,
One in New Park, it was called the
I know that.
Right enough is what
It was just like this, it was really small videos. But it was. I wish I had known about it. There was like, there's a really good library.
I remember in high school.
I wish I would have known about that. That was Saturday the day before. Yeah, there's a trigger back with my school.
I had to work. I don't know. What was it for?
It was cool.
Oh,
I'm a little more. That's what I'm saying. I wouldn't have heard it. I heard about it other than this guy in the Volkswagen bus came up to me. He's like, "You better be there, Missy." And I was like,
That sounds so.
That's what I'm saying. At first, I was like, "What?" And then I read it, and I was like, "Hey, he's probably cool."
Why did he come up to you?
Alright, so x-axis motion. A little bit harder to visualize, but we talked about yesterday, visualize a pinball. It can go in any direction it feels like. It can stop, it can pause, it can continue in the same direction, it can turn around. Has anyone never seen a pinball machine? Okay, good. That's what I used to do in between classes when I was in college. Back in the olden days before cell phones. Alright, so,
I just thought you were saying.
still gonna use derivatives, and the relationships should still stay the same. Instead of s, when it's x-axis motion, a lot of the times they'll use an x to let you know, okay? The derivative, x of t is the position, the derivative position is still velocity, the derivative velocity is still acceleration, okay? So those relationships don't go away, it's just the type of movement is different. So far, so good? Okay, and we talked about that yesterday. Okay. This one's pretty important, and this I was never actually taught. The first time I saw this type of question asked on an AP exam was about 12 years ago, and all I could figure out, well, I finally figured it out, but I wasn't sure if my logic was sound. So I was like visiting all the science teachers in the building, to try to figure it out, and it was. Here's the deal. A lot of times they will ask you at a certain time t, like at 2 seconds, is the object speeding up or slowing down? If you can figure out the acceleration at time 2 in this example, and the velocity at time 2, well, you need to know if they're the same sign, it means that they're working together and the object is speeding up. If they're opposite signs, it means they're fighting against each other and the object is slowing down. That's the way my brain kind of figures it out. It's either one's pushing the other along and they're working together, or one's kind of holding the backpack of the other one and slowing it down. Good? Okay. So, here we go, our first example. We have a position function. Notice it's no longer quadratic, x-axis motion. You can either tell by the function if they happen to rudely still use s. You can tell by the function if it's not negative 16t squared or negative 4.98. I don't even remember, half of 9.8. You can kind of tell. It's a cubic function. Okay? So write the velocity function. How do I go from position to velocity? The derivative. So that's going to be 3t squared minus 12t plus 9. The relationships still hold true. The acceleration function, how do I get to that? Take the derivative again. So 6t minus 12. So notice for these problems, the majority of the time acceleration is not going to be a constant because it no longer represents gravity. So far, so good? Okay. When is the object at rest? What do we know about this phrase? It's not moving. And if it's not moving, what's true? Its velocity is 0. Does that make sense? Especially to the non-physics people. Does that make sense? Okay? When we see the phrase at rest, that means that the velocity is 0. Every time. Okay? So we take the velocity function, which was 3t squared minus 12t plus 9. Did I remember that right? Set it equal to 0. And then you can use your graphing calculator, you can use the quadratic formula, it doesn't matter to me what method you use. Solve that equation. Just like before, we're not going to deal with negative values of t. However, it could be that we get multiple positive values of t. Because remember the pinball in your head. It can just pause. You know, it has those little round things that are little magnets or whatever that make it stop. You know, it can pause and then it can go and then it can pause again and then it can go. You know, so it can do like really weird things.
I got negative 9 and negative 3. Yeah, it would be
I
negative
got
1
1
and
and 3. I got 1 and 3.
Yeah, negative 1 and 3. Yeah, that's what
Positive called you a goof. Okay. I want you to graph it though. We're going to talk about the graph a lot. So if you haven't graphed it, go ahead and graph it. The position function. And we're going to start using this section. Oh, error, great. You see that? We're going to start using this section to give us insights on some future sections, and it'll be a whole lot easier when we get there.
So what was the answer?
We haven't answered it yet.
No, I'm just, like, what did they get?
I don't remember what they got. Somebody tell me what you got.
1 and 3.
1 and 3.
Okay. Would you read me the position function? And remember to use x's.
Oh, okay. T cubed minus 6t squared. Oh, x. Yeah, sorry.
Okay.
Plus 9x minus 4.
Okay. Did I type it in right?
I forgot the
Yes.
Alright, so this is our position function. So let's start hopefully making some connections as we go through and answer these questions.
It's not the equal 0 part.
There you go. Nice you figured it out. Alright, so this is position, it's a cubic function, right? And we know that velocity is the derivative. And we know that the derivative is the slope of the tangent line. So look right here. At t equals 1, or in this graph x, isn't the tangent line horizontal? What's the slope of a horizontal line? 0. So does it make sense that if you've got the position, the top of a hill would represent when the velocity is 0? And the bottom of a valley as well? So looking at the graph, we know we've got two places where the velocity is 0. Okay? And we can calculate that on the graph, or we can calculate it on the calculator screen. It doesn't really matter to me, but I'm thinking 1 and you said 3 sounds reasonable to me. Does that make sense?
Yeah.
Do I need to go through getting 1 and 3 with anybody? Going once, twice? So we're going to keep that graph. So at t equals 1 and t equals 3 seconds. Oh, wrong one. Sorry. Thank you. I know. Just think of a pen. Yeah, I might force you to go play pinball for homework. Find a pinball machine. Do they make those for phones? I'm sure they do.
Yeah.
It's not the same.
It's not the same experience.
Yeah, they did.
And you don't get to shake the machine when it doesn't do what you want it to do. Alright. When is the object moving to the left? So remember, with parabolic motion, we talked up and down. If the velocity was positive, it was moving upward away from the earth, and the velocity was negative, it was moving downward. Okay? So, let's think about this. Left. Well, what do we know about the velocity? Negative. If you had to guess, right, left is negative and right's positive. And so for right, I'm going to look at both of these at the same time. Velocity is going to be positive. Does that make sense?
Mm-hmm.
And we're going to find that, but I want to look at the graph because we got a couple different ways we can do it, and it's really kind of neat. Okay? Velocity, remember, is the derivative of position, correct? Okay? So, derivative is slope. Let's look right here. Is the slope here positive or negative?
Positive.
So the derivative is slope and the derivative is velocity. So right here, velocity is positive. What does that mean about the graph? Which way is it going?
Right.
Right. And here, the slope is negative, so velocity is negative. What does that mean for the graph? It's going left. And then here, velocity is positive, so what does that mean? So it's going to start off, remember we're not looking at the negative values of x. It starts off moving to the right, then it stops. Then it starts moving to the left, and then it stops. And then it continues moving to the right forever. Right? It doesn't stop anymore. Does that make sense? Okay. Here's what I want you to do. Get you a second graph page just to make connections here. On this second graph page, what I want you to do is I want you to graph the velocity function. Okay? The velocity function was 3t squared, so 3x squared minus 12x plus 9. 3x squared minus 12x plus 9. Did I remember that correctly?
Yes.
Thank you. Now, remember, this is velocity. Velocity positive means above the x-axis. So we've got two intervals here where it's above. Velocity negative means below the x-axis. So it leads to the same conclusion. Both of these graphs, and at some point you just have to figure out which graph makes the most sense to you. Because sometimes on the AP exam and on questions, I'll give you a graph and it'll say this is the position function. Or this is f of x. And then sometimes it'll give you a graph and you have to say this is the graph of the derivative, or in this case the derivative is velocity. So you have to kind of understand the relationship between the two.
How can we derive that algebraic?
I'm going to show you. Okay? All right, so here, using the graph, we could find these roots. Okay, so let's do that. Menu, analyze graph. Zeros, roots means the same thing. And you just have to kind of get here. Now, we have figured out already that the velocity is 0 at 1, right? So think about most of the work we've already done here, but I want to back it up. Okay, and we could do the same thing here. Menu, analyze graph, zeros. So, from 0 to 1, the velocity is positive, so it's moving to the right. From 1 to 3, the velocity is negative, so it's moving to the left. And from 3 to infinity, okay, the velocity is positive, so it's moving to the right. We get the same thing on this graph by finding the maximums and the minimums, which we've already found. Do we know how to do that on the calculator? Or has it been a while? Let's go through and do it. Menu, analyze graph. Our first one's a maximum. You just have to get it in the crosshairs there. We're coming across these same values. Menu, analyze graph, minimum. So if we're looking at a graph of the position function, its slope is positive, so its velocity is positive from 0 to 1. Its slope is negative, so velocity is negative from 1 to 3. And its slope is positive after 3, so it's moving to the right after 3. Same information, two different graphs. By hand, here's what you would do. Okay? We already know that at 1 and 3 that it's at rest. Okay? Those are the important places. Notice those are the places we found on both graphs. No matter which representation we used, we had to know those values. Okay? So, let's get us a number line. I'm going to do it on a separate page. You've got border though, right? Yeah, you've got more room than I do. All right. 3t squared plus 9? Okay, that's our velocity function, right? Let's start thinking in terms of number lines. We're going to use those a lot. We know that at t equals 1, the velocity is 0. We found that already when it was at rest. Even if they don't ask you the at rest question, you have to find when it's at rest to figure when it's going to the left and when it's going to the right. Because remember, it can only transition from one direction to the other if it stops. Okay? So we know that there's no other time that this thing is going to stop, or it would have popped up in our algebra, or quadratic formula, or the calculator. So we know that there's no other time it's stopping. Now we know that we're going to stop this number line at t equals 0 in context, right? But we know that clocks keep ticking, so we're okay with that side. We test a value right here. Any value in between 0 and 1 should give us the same conclusion, because I know it doesn't stop in there. So we would test any number in there, a half. Plug it in there, okay? Or you could use the graph, okay? If you're plugging it in by hand, using the calculator, that's fine. You're going to get a value. Or you can let the graph help you out. This is the velocity. At a half, it's positive. You could use trace. Menu, trace, graph trace, 0.5. I don't care that the value is 3.75. All I care is that the value is positive. And I know that positive means that it's moving to the right.
Positive meaning above the x.
Yeah. I'm looking at velocity. I always label my number line so I know what I'm talking about. Velocity, positive, means it's moving to the right.
Even though it's going down.
No, the original, you got to remember what graph you're looking at. at a half, it's positive. Okay? And it stays positive until it gets to 1, which it turns to 0. Okay, let's just kind of roll with it. Are you okay that the velocity at time 1/2 is a positive number? Yeah, you're okay with that? Okay, and you know that velocity gives direction, either for parabolic motion, projectile motion, up or down, for x-axis motion, left or right. Okay, so if the velocity is positive, which way is it going? Right. Okay, it doesn't matter. I could have picked 1/4. I'm still going to get a positive number, which still tells me the velocity is positive. It's still moving to the right. You have to be careful with the word it. Okay? All we care is velocity positive or negative in that interval. Okay? Better? You get there. You just have to practice it. Okay? So in that interval, no matter what number we pick between 0 and 1, don't pick 0 and 1, okay? No matter what value we pick between 0 and 1, we're going to get a positive number. You can test any one you want, you're going to get the same result, it's going to be positive. Okay? Between 1 and 3, what's the easiest number to pick? 2. So let's go on the velocity graph, because I'm using a velocity number graph. 2. I get negative. What if I decided to pick 1.5? Still negative. What if I decided to pick 2.5? Still negative. Could I pick 3? No, because I know at 3 it's 0. That's when it's at rest. So anywhere I choose between 1 and 3, the velocity is negative. What does a negative velocity mean for movement? It's moving to the left. Yes, ma'am. Yes. Okay.
So then we can do this for acceleration also, and see when it's
Yes.
see when the speed
Yes.
is like that.
All right. I need to pick something to the right of 3. What's the easiest thing to pick to the right? 4. So trace is the easiest place to go, just because for right now in the beginning, our eyes need to see actual negative values or actual positive values. We'll get to the point where we don't need to do that. We'll just go, hey, it's always below, it's always above. If we're looking at the plot, you have to remember which graph you're looking at. Okay? So we tested 4. I get a positive number. What if I decided to pick 9? Still a positive number. What about 4.5? Still a positive number. Different velocities, okay, which means it's not the same speed as it was. It's speeding up or slowing down or whatever, but it's still a positive velocity, so it's still moving in which direction? To the right. Feeling okay? We're just starting. We're 2 days on x-axis motion. Okay? Alright? So, we know from time 0 to 1, it's moving to the right. So, moving to the right from 0, brackets are poor form, sorry. At 0, it's not moving to the right. From 0 to the 1, this is an interval. It's moving to the right. I tend to answer both these questions at the same time once I get my number lined up. I just go left to right on my number line. So 0 to 1 second, it's moving to the right. From 1 second to 3 seconds, it's moving to the left. And I got in the habit a long time ago, if I didn't write the word test here with this number, I'd try to put this number in my interval. I have to write the word test with it or I get it mixed up. Okay? And I have to put these zeros here to remind me that that's when it stops. Okay? So from 1 second to 3 seconds, it's moving to the left. And then from 3 seconds on to infinity, it continues on to the right.
Do we have to show that in intervals, or can it be like?
You can write it out in words, you can write it out in inequalities, they accept any notation.
Could 1 and 3 be brackets?
No, and here's why. At 1 second, and that's why I put brackets and I had to erase it, so that's poor form. At 1 second, it's not moving. It's at rest. And I've seen probably 3 examples on the AP exam when they use brackets and they shouldn't have it. It makes me just angry. Because sometimes on free response, they'll count off for that. Okay? Now that we've got all this information up here, it makes it really easy to answer question number 6. Does the object ever change directions?
Yes.
Yeah, when does it change directions?
1 and 3.
At time 1 and time 3. It stops and it changes direction. Sometimes it stops and it keeps going in the same direction. So yes, at time equals 1 and 3 seconds. S looks like an 8, but I'll know what it means.
So because applications, we don't ever have negative infinity for x.
No, because, well,
So-
when, yeah, especially not motion, we have to stop the number line at 0. Okay? Yes?
I get for number 5, I get like the 3, and everything, but why is it the 0 for the 1?
Because from 0 to 1, we stop our number line at 0. At 0 to 1, we know it stopped at 1 because the velocity was 0. And when we picked points in between 0 and 1, all of them were positive.
Oh,
So that
we
meant
can't
it was
go-
moving to the right.
We can't go past 0, we can just go into the right.
We're measuring time.
I got you. Okay, thank you.
You're good. Awesome. Thank you. I didn't realize that was the question she was asking.
I didn't know what question was asking.
We okay? All right. What is the distance traveled by the object from time equals 0 to time equals 5? Here you have to be really careful. Okay? A lot of people will plug in time 0 to the position function to see where it was at time equals 0. And they'll plug in 5 to the position function to see where it was at time equals 5. And then they'll subtract those two numbers to see how far it went. But we have to remember, this sucker turned around. That's like saying that if I walked to here and then walked back to here, I didn't go anywhere. Well, my Fitbit will tell you different. Just like my Fitbit thinks I'm jogging when I erase the board, which makes me laugh every single time. At college, I'll be doing something, I erase the board and I'll just laugh because my Fitbit thinks I'm jogging. Alright, so, yeah, there's a difference. In physics, they call it the difference between displacement and distance traveled.
Yes.
Is that what they call it? Okay. In calculus, we almost always deal with distance traveled. Okay? Think about it with this number line. We know that from 0 to 1, it's going to go somewhere. And we have to figure out how far it went. And then from 1 to 3, it's going to go some distance. And we have to figure out how far it went, even though it turned around. Okay? And then the same thing from 3 to wherever. Now, it's going to give us a specific interval because we can't plug in infinity, and I don't remember what the interval was. What was our interval?
0 to 5.
0 to 5. So we have to start here, and we have to stop right there. Okay? So, first we need to figure out how far it went from 0 to 1 and give it credit for that. Right? So let's do that. So let's first look at its position at 0 and its position at 1. Now, work smarter, not harder. There's a reason I told you to put your position function on a graph. Okay? Use trace. Graph trace 0, graph trace 1 for the position function. Make sure you're not on the velocity function. Go back to the position function. It's going to be really, really important to remember where you are. They are really bad, good, I don't know how you would classify it, for using the velocity function to answer this as their bait questions, their bait choices on multiple choice. Because they wanna know, do you know where you are? Alright, so what did we get for position 0? -4? Now, some people say, okay, wait a minute, we can't have -4. Remember, this is x-axis motion. That just means it's 4 units left of the origin. Okay, so be careful with that. It's not time, it's position. What's s of 1? 0. So in that interval, how far did it travel? 4 units. So it started off at -4 on the number line. Think of it that way. And it traveled to 0. So it went 4 units. Good? Now we know that then it's going to continue on to 3.
But don't we like take until the vortex and then back to 3 because
Say it again.
oh no never mind, I'm sorry.
Okay. Just think of it as steps. Okay? At S of 3, use the same graph. Menu graph, trace 3. What'd you get?
-4.
Go to menu, settings, I believe it's option 9. That yours probably says float 3. Tell it to float 6. Anytime it gives you something weird like that, that's exactly where you need to look. And then go down the bottom and hit OK, and it should be right. Now, what does it say? -4? We agree? -4? So, if we were only looking at this one and this one, we'd think it didn't go anywhere, right? So we know it went 4 units here, and then it revisited where it started. So how many units did it go here?
8 units. Oh.
I'll get there. Yeah, you're answering the next question, which is fine. Okay? And then we know then it continues on forever in the same direction, but we don't need forever. It told us where to stop looking. Where do we stop looking? So for trace, what'd you get for 5? 16. Oh, it really trucked on then, right? So from -4 units to 16, how far did it go? 20.
So which graph are we looking at?
Position.
'Cause
We're looking at where it is.
But I'm not getting it right for the, like I have negative.
I know, it's hard to put that to numbers unless you want
It's x squared minus 6. You've got time.
Let me
So I would pick that up.
Alright, so how far did this sucker travel in those 5 seconds? 28 units.
Is it in or is that?
Just units. They don't tell us. I'm sorry. Just think of the number line. It's units.
I have a question.
Uh-huh.
The whole time you've been talking about the graph going, or the pinball,
Yeah.
I guess, going
That's
left,
for me, that's how I have to visualize it.
going left and right,
Uh-huh.
when the graph is just going right the whole time.
Well,
You're gonna turn sideways.
yeah, so we have to force our graph to match like a pinball machine, which is not really possible. We just have to deal with positives and negatives, and what does that mean?
So we're paying more attention to the numbers and less to the graph itself.
Well, we use the graph to get the numbers
Yeah,
to help us
but-
out, but yeah, you have to. we have to start trying to make the connections between the numbers and the graph because it'll be helpful. You can do this without the graph. It's a lot harder. And this way we start going, okay, negative velocity. If I'm looking at a graph of velocity, that means when it's below the x-axis. If I'm looking at a graph of position, that means when it's going downhill. We have to start making those connections. Positive velocity, if I'm looking at a graph of velocity, it's when it's above the x-axis. If I'm looking at a graph of the position function, it's when it's going uphill. So we just have to kind of start trying to make that work together for us, which is why we spend one and one down, because it's a hard bridge for some of us.
Because the other one, the one we did yesterday, it shows like the exact path.
Oh, yeah, because it's, yeah, that's parabolic motion works that way. Alrighty, we okay? Alright, displacement. I tend to usually ask the distance traveled before displacement, and we don't always ask it in calculus, but I want to make sure you know the difference. Displacement is how far it ended from where it started. It started at -4, it ended at 16. How far did it end up from where it started? 20.
20, that's so weird. It ended 20.
Okay? That would tick me off because that means I went 8 places that I didn't get credit for. You know? You don't want this on your Fitbit, you want this on your Fitbit, right? It's a new technology to explain things, it's nice.
Shouldn't it be 16?
It started at -4
Oh, sorry.
and it finished at 16. Okay? Now our brain wants it to start at 0.
Yes.
That's what it is. That's why I'm very visual. If I didn't write that down, I'd go 16. Good?
And can we use that formula of like s of 5 minus s of 0 over 5 minus 0?
For average velocity. Alright, at 2 seconds, is the object speeding up or slowing down? What, excuse me, what 2 pieces of information did we need to answer that question? The velocity and acceleration, not just any velocity and acceleration. Velocity and acceleration at time equals 2. Excuse me. So we need v of 2 and we need a of 2, right? What was somebody with the v of t function pretty close by? What was the v of t function?
3t squared minus 12t
12t.
plus 9.
Okay. Now, since we've got the velocity function graphed, you can go to the velocity function and just type in trace and get that number. Okay? Once again, all I care about is whether it's positive or negative. I don't really care about the actual value of the number. Okay? And then the acceleration function was 6t minus 12. That's kind of working from that. Oh, that's a weird one. Okay. This one, what did we get? Positive or negative? 2, velocity was negative, wasn't it?
Yeah.
Okay.
Velocity function.
Is 0 considered even?
Yeah, well,
It's not.
Has a
Wait, I don't know why I
constant
don't know why I
velocity.
said even. I meant
It's the point at which the velocity changes
hold on.
direct
I don't know why it's even.
quote unquote directions.
Alright, so this thing didn't pop up, which I wasn't expecting that. I haven't worked this ahead of time. This thing didn't show up in our thing, but let's think about it. This thing moves to the left, and this isn't doing anything to it. Anybody ever used cruise control on their car? Constantly.
So I don't.
I like that you use the word constant. It helps me out there. Okay. the cruise control controls your accelerator, right? Okay, so at that moment, it's not speeding up or slowing down, it's maintaining the same speed. Does that make sense to you? Okay, because this says that your cruise control is not letting it change. That's what that means. So we will say neither maintains the same speed. Now, what if we'd have gotten a negative number for acceleration? What would we say?
Speeding up.
Speeding up, because they're the same sign. What if we'd have gotten a positive number for acceleration? What would we say? Slowing down, because they're working against each other. Yeah.
Like, but isn't the velocity only constant at 1 and 3 seconds?
The velocity is 0 at 1 and 3 seconds.
But how's the
That means it's not moving at all.
but how's the velocity constant at 2 seconds?
Well, at time equals 2 and no millionth of a second either way. At time equals 2, the velocity is some number. The speed is some number. It's not stopped, it's still moving. So we're going to get a number for how fast it's going. We get a totally different number for 2.4 and a totally different number for 1.9. But at 2, we can get a number for how fast it's going.
Okay.
That
So
make-
you can't have an acceleration at 1 and 2.
Well, yeah, we got acceleration at time equals 2. Let's answer the question for 1.5. Let's do that. Maybe that'll clear things up for you. At 1.5, I'm going to use a graph of velocity. And are we still on trace yet? At 1.5, the velocity is negative, right? Okay. At 1.5 here, that would be negative, right?
Yeah.
Okay. So negative and negative, what's happening to it? Speeding up. Okay? It's just that when it gets to 2 seconds, for just a moment, it's maintaining the same speed. Okay? Better? The minimum was at 3. At time
Two
equals
is
3.
kind of like right between the two places it stops, so it's like the only place that it's.
Two is the
Tangent
minimum.
line is not cycle because it's.
Yeah, that's what I'm saying, that's why I was on,
Which graph are we looking at?
the velocity ones, because it comes to a stop. Or
Okay.
it's like slowing down so it can speed up again.
Yes. I was thinking you were talking about the other graph. Okay? Good. So here, velocity is negative, acceleration is negative, it's speeding up. And then it briefly, what's happening?
I just saw that, I'm sorry,
Oh.
I got just distracted.
Yeah, I don't know. I think that was the same group that one girl thought my name was Howdy. All right. I don't know. So here, velocity is negative because it's below the x-axis. Acceleration is negative because it's decreasing. Okay, so it's speeding up. Here it has to maintain for just a second. And then here, velocity is still negative because it's below the x-axis. Acceleration is positive, so it's slowing down to get to a stop. Make more sense? So that's why I think the graphs help a lot.
So being negative, like, so it doesn't matter about the slope. Like, what I'm confused about is, like, is it the negative, like, below the x-axis, that's making it go left, right?
Are you on the velocity graph?
Either graph.
No.
Wait,
It depends on what graph you're on. Below the x-axis on the velocity graph means velocity is negative, which means it's going to the left. So I think you're on the velocity graph.
yeah, and then, so if it's, so what about the other graph?
The other graph was the position function.
What does it mean if it's negative?
Okay, think about this. Let's look at it. Position function means where it's at.
Right.
Okay, we knew when we plugged stuff in that at 0 was at -4. That tells me where it is. The position tells me the position. So at 0, it was -4. At 1, it was back at the origin. At 3, it was at -4 again. That's where it is on the x-axis. Okay? We'll get there.
So,
What time is it?
You got like 5 minutes.
Huh?
so the other one is velocity, so that means the speed, or,
Velocity will give you speed and direction.
and this is just the
Position. Okay? Alright. You need to help me remember that we are here, and I need to remember to stop there for the next group so we're in the same place. Alright, I'm not posting any new problems tonight. I'm gonna wait till tomorrow.
She got her loan. Good job, financially stable.
Better idea.
I love whenever I start